Okay, we want to complete our problem that we started in the last class, which was diffusion of A through a stagnant gas. And you recall our system was either a cylinder or a cuvette that contained liquid A at the bottom, and it was diffusing in the positive Z direction, and the location at the gas-liquid interface was Z1, and the top of the column was Z2. The mole fraction of A was specified at the top as XA2, and then the mole fraction of A in the gas at the gas-liquid interface is known as XA1, and that follows from the thermodynamic problem at the interface where we assume local equilibrium of A between the gas and liquid phase. So we were at step 6, which is simply the math step, and we had obtained the simple differential equation that dxa dz was equal to minus C1 times 1 minus XA over C dAB. So the procedure is always to simply classify the differential equation so we know how to solve it. And in this case, it's quite simple. It's first order, and it's also linear. So we have a simple cookbook method to solve all first order linear differential equations, and all we have to do then is put this equation in its standard form and then write out the solution. So you'll recall our standard form of a linear first order differential equation look like this. And so for our case, the dependent variable is XA and the independent variable is Z. So we have dxa dz minus C1 over C dAB XA is equal to minus C1 over C dAB. So we clearly identify the parameters P of Z is equal to minus C1 over C dAB, and also the non-homogeneous term is C1 over C dAB. So we can go directly to now our solution and write it down. And to make this a little easier, we'll introduce a C1 prime, which will lump some constants together. We'll let C1 prime equal to a negative C1 over C dAB, just so we don't have to carry those constants around with us so much. So the solution then, from our Shams book that we've highlighted, is a new integration constant that we'll call C2 times exp of minus C1 prime Z. And then we have the non-homogeneous term, and exp of minus C1 prime Z times the integral of C1 prime times the exponential here of a plus C1 prime Z, and that's all integrated with respect to Z. And that, again, that integration is done indefinitely. So this is simple enough. We get immediately that XA would be equal to C2 exp of minus C1 prime of Z, and the non-homogeneous term just gives us 1. So now all we do is apply the boundary conditions of the problem to determine the unknown constants C1 prime and C2. So this is how we always proceed, integrating indefinitely, introducing arbitrary constants of integration, and then use the boundary conditions to determine those particular constants. So we can rewrite our equation to obtain the Book's form of the solution by introducing logarithm in place of the exponent. So we can do that by simply taking the log of both sides of our equation. Now this is minus C1 prime Z. So take the natural log of both sides, and we get the log of 1 minus XA is equal to, and we'll replace the log of minus C2 with a new constant, just call it C2 prime, and then the log of the exponential gives us the argument of the exponential back, so that's minus C1 prime Z. And boundary condition 4a tells us then log of 1 minus XA1 is equal to C2 prime minus C1 prime Z1. And boundary condition 4b similarly tells us 1 minus XA2 is equal to C2 prime minus C1 prime Z2. So we have two algebraic equations with two unknowns, C1 prime and C2 prime, and so we simply just have to solve these equations simultaneously to obtain those particular constants. So there's different ways you can approach this. The easiest thing would be to subtract 4b from 4a, and therefore we would obtain the log of 1 minus XA1 divided by 1 minus XA2. And the C2 prime cancels, and on the right hand side we'd have minus C1 prime Z1 minus Z2. So then that gives us then our first integration constant, C1 prime. And then we simply can put that back into either the top equation, 4a, or you could put it back into 4b to determine the second integration constant, C2 prime. So either way is correct. Okay, so we've rewritten the first integration constant, C1 prime, and then C2 prime, again, follows from equation 4a, so that would be log of 1 minus XA1 plus C1 prime Z1. And so this is just simply substituted, the top equation is substituted in for C1 prime and thereby obtaining C2 prime. Then both of those constants are put back into our original solution for the concentration profile, and therefore we can easily show that the profile would look like this. Log of 1 minus XA over 1 minus XA1 is equal to Z1 minus Z over Z2 minus Z1 times the log of 1 minus XA1 over 1 minus XA2. And we can absorb the constants, absorbs the signs rather, by noting that the log of x over y is equal to minus the log of y over x. So we can rewrite the right-hand side of this equation as simply z minus z1 over z2 minus z1 So now those are positive quantities. And then the log of 1 minus xa2 over 1 minus xa1. So this equation then is the desired concentration profile written in terms of the logarithm. Okay, so we can get the Book's form by exponentiating both sides of that equation. And that is raised to the z minus z1 over z2 minus z1 power. And that's the equation given in the text for the concentration profile, which gives the mole fraction as a function of z. So we can also obtain the flux, NAZ, quite simply because we know that NAZ was C1, and we had that C1 was equal to A minus C1 prime times C dAB. And we have determined C1 prime already, so just by direct substitution we obtain the flux as C dAB 1 over Z2 minus Z1 times the log of 1 minus XA2 over 1 minus XA1. And that is the flux expression given in your text. So again, the goal was to integrate indefinitely, introduce arbitrary constants of integration, and determine those arbitrary constants of integration from the boundary conditions of the problem, thereby obtaining the concentration field, and then going back to our flux expression to determine its particular form based on those constants of integration. So the only thing left now is step 7, which is to check the boundary conditions in the units. So we can verify that the units here indeed give us a flux, and we can look at the concentration profile given by this expression to prove that that indeed satisfies the boundary conditions of the problem. Step 8 is the implications, and for this particular problem is quite interesting. This simple model here allows us to set up an experiment by which we could back calculate the binary diffusion coefficient from measurements of the flux. And so we'll talk about step 8 in class, but in the meantime try to complete step 7.